Hello everyone. This is the lecture on the second module of first week. So what we will be seeing in today's lecture, we'll look at what it means to test a software. What is testability? We will also look at what is model-based testing as it's commonly perceived in the testing world and how we will use model-based testing when we design algorithms for test cases. As I told you, a lot of this course is going to be on algorithms and methodologies for test case design. And in fact, we'll be looking at what is called criteria-based test case design. So we'll formally define what is criteria and look at the various artifacts on which we will be defining these criteria to design test cases for. So I begin with introducing what is testability. So what is testability? If you look at it in simple English terms, it simply answers the question, is the software testable or not? So now if I ask the same question again in turn, what does it mean for the software to be testable, right? So we say, can I give inputs to the software, inputs as test cases to the software? After giving the test cases to the software, can I execute the software and observe the outputs? You might think it's a very obvious question. When I write a piece of code, what is the difficulty about giving inputs to the software, executing the software and observing its outputs? So we'll see what are the particular hiccups that can arise while doing this. Two related notions of testability are what are called observability and controllability. So what does observability mean? Observability tries to answer the following question, right? So it says that suppose you give a software certain kinds of inputs and execute it. How observable is its behavior? How observable are the outputs that the software produces? It could be doing a lot of things silently and producing only the final output. Whereas as a tester, you might be interested in some intermediate outputs that the software produces, right? So observability tries to answer this question about how observable the outputs produced by the software are and how much we can tweak the outputs that we want the software to produce towards testing it. So when I test a software, I might want to observe a little more about its outputs, not actually the actual outputs of software, but I might want to know the values of specific internal variables, specific call and return values. Observability deals with all this. Another related term for testability is what is called controllability. What does controllability ask? Controllability says, is a software controllable by giving it some input and actually executing the software? Again, this might seem like a trivial question. You might ask, why is it so difficult to give inputs to a software, right? Let's take a particular case, for example, where a piece of software runs for some time and then at a particular point in code, it calls a particular function, right? So I want to be able to, let's say, integrate, test this function call. So what I'm interested in controllability is the fact that I should be able to give inputs to the software such that I can ensure that the particular function or procedure that is embedded deep inside the code is actually called for the values of the inputs. And not only is the function called, I want to be able to observe what the function returns in turn. So controllability and observability help you to answer these questions in software, and they are one of the several different quality attributes, broadly called ilities, that people worry about while testing and writing software. So to define test inputs and to ensure that an appropriate part of the code is reached, like I told you, an appropriate function is called and I will be able to in turn observe the value returned by the function, I say that the software needs to be controllable. When I want to observe the value that is returned by the function and see how it gets passed on to the main callee program, then I say that the software needs to be observable. Observability and controllability put together constitute testability of a software. Obviously, for a software to be testable, its testability quotient must be very high. It should be observable, it should be controllable. So we will little more in detail understand what these notions are. When people say a software is testable, they usually talk about 4 parameters for observability and controllability put together. So these 4 parameters are what are called the RIPR model. So what is R? R stands for reachability. Reachability means, suppose I'm testing, white box testing a piece of software, and I want to check whether a particular statement is reached, whether a particular function call is reached, whether a particular code segment is reached. I should be able to give test inputs that guarantee the execution of software in such a way that this particular target place in the software or code is reached. Now, the next important thing is I. I stands for infection. What do we mean by infection? Not only do I want to reach that place, I want to be able to execute those statements in the software. And suppose there is an error that is observed, I want the error to be exercised, or I want the error to be reached. I want the software to reach its faulty state, right? And I want to be able to give inputs in such a way that I can infect that particular statement in the software and actually pull out the error or the faulty state the software was in. Suppose I manage to do that, but the software still manages to run fine and execute such that it acts normally. Then even though the software is erroneous, I as a tester haven't really observed the error, right? So the next parameter that I'm looking for is P, which stands for propagation. So I say not only must the particular statement be reached and the error be revealed as infected, the error should also be propagated to output, observable output, such that I know that there is an error that has occurred in the software. And it could be propagated, and for some simple reason, like you might have just forgotten to write a printf statement or forgotten to track this particular value, the propagated error might not actually get revealed to the tester. So the last parameter in this RIPR model that I'm looking for is for the error to be revealed. This tester will be able to observe the incorrect part in the program and correctly isolate and identify which part of the code was the error in. So to summarize, we say that if I am targeting a particular piece of code that I suspect to be erroneous or that I want coverage to be achieved, somebody told me, you please test this piece of the code thoroughly, you please test this function and the function call thoroughly, right? So I'm looking for 4 properties that the software should satisfy for it to be observable and controllable. The first one is that the particular target code fragment or segment should be reachable. The particular target code fragment or segment, if it has an error, should infect, and the particular test case that I give should make sure that the error state has actually occurred. This occurred error in turn should propagate to the software producing a different kind of output that reveals the error. And the revealed error should in turn help the tester to be able to identify and isolate the error as having occurred in that piece of software. So a software that meets these RIPR model property is supposed to be highly testable. So here is an example of an RIPR model. You consider the small code fragment that is given here. I have not given the full piece of code here. I have just given a small fragment of the code. In this small fragment of the code, there are 2 inputs, X and Y, and then there could be other statements, a lot of other commands in the software. But let's focus on this particular thing, fragment of the code, which says that there are 2 nested if statements here. The first statement checks if X is less than 10, that it sets the value of Z to be X plus 1, and then there is one more if inside that, which says that if Y is less than Z, then there is an error in the software. I haven't actually written what the error could be. I have just written it like a stub, which marked it out as error, right? So suppose I want to actually, my goal is to be able to actually reach this error statement and reveal the fact that this error has occurred. Right? So what does RIPR parameters do for this? So let's look at reachability first. So what does it mean for the first if statement to be reachable? Any value of X will reach that statement, right? Assuming that there are no code fragments that change the value of X, any value of X that is given here will reach the first statement, which is X less than 10. So reachability can be thought of as being true, always true. There's nothing specific that I need to do, right? But to be able to reach the second nested if statement, suppose the first if statement tests negative, in the sense that suppose I give a value of X that is not less than 10. So this predicate will return false, and the code will exit this if statement. It will never enter this if statement. If it doesn't enter this if statement, it is not going to be able to test the second if, make it positive, and then reach the error statement, right? So reachability for the second if statement will happen only if the first if statement returns true. And the first if statement will return true if I give a value of X that is less than 10. So the predicate X less than 10 should be true for me to be able to reach the second if statement, right? So what is infection? Infection means I not only reach the statement, I manage to execute that statement and make it true or false. So again, infection for the first if statement is any value of X less than 10, like for example, or any value of X greater than 10, or even X is equal to 10. will manage to infect this first statement. For the second statement, remember z is set to x plus 1. So you must give a value of y that is less than x plus 1 to be able to test the second if statement. Now moving on, when it comes to propagation, I should be able to go past the first if statement, make it true, go past the second if statement, make that also true, and then only I will reach the error statement. So both these predicates, x less than 10 and y less than z, will have to be true for me to be able to reach the error statement. So I hope what reachability, infection and propagation is very clear. So in this piece of example, it's quite small, so it was easy to be able to do what are the conditions for reachability, infection and propagation and so on. But for large fragments of codes where I have thousands of lines of code, it's not an easy problem to be able to come up with list of predicates for reachability, for infection and for propagation, and to be able to solve them. In later modules, when we look at testing criteria, we will see what it means to solve a predicate or a particular piece of code for reachability, for infection and for propagation in detail. I'll now move on to looking at model-based testing. What does model-based testing mean? In the English sense of the term, model-based testing means that you have a model of the software artifact. The artifact could be requirements, it could be design, it could be architecture, it could be code. And then you design test cases by looking at the model. There are, of course, several other uses of the models for software. Well-done models could be used to auto-generate code. They could be used to early validate the system. There are several other uses for model-based design and model-based testing. Right? There are broadly two kinds of models. The model could be based on a formal mathematical notation. Here are some popular modeling languages: finite state machines, graphs, logical formulae, right? As I told you in the last module, there are several different verification techniques like model checking, theorem proving. They all use mathematical models of software artifact to be able to verify a software. Models could also mean a particular domain language or a specifically designed language that specifies all the artifacts that a particular software is concerned. You might have heard of popular modeling languages like UML, which stands for Unified Modeling Language, SysML, which is Systems Modeling Language, Simulink, Stateflow, which are modeling languages that are proprietary to a company called MathWorks, which makes a popular tool called MATLAB. So these modeling languages support several diagrammatic notations for me to be able to model various software artifacts like use cases, requirements, design, control laws, and so on. They may or may not have formal semantics, right? So it is to be noted, as I told you, that the model need not be only for code. It could be for requirements, it could be for design, and so on, right? Testing with models for requirements and design. Suppose I manage to have good, well-defined models for requirements and design, and I'm able to design test cases for them. Then remember that I'm doing this kind of testing right at the requirements level or design level before I write code. So if I find an error, I find it early on in the life cycle, and that is considered to have lots of benefits. So what is the process of model-based testing? How does it work? Right? Let's begin here with this part. I have a software artifact with me under consideration. That could be code, that could be a requirements document, that could be a design document. Right? Code is typically executable, but many software companies have requirements of design document written in English, right? So English documents cannot act as models. So I take the software artifact and come up with a model of the artifact, right? The model of an artifact is designed in a language that I have predisposedly decided is suitable for the class of software that I am working with. Once I have the model of this software artifact, I do what is called model-based design, and I can subject this model to several different uses. But what we will focus on today is, in this particular slide, is the use of the model when it comes to designing test cases. So I take this model of the artifact, and then I also have a set of test requirements that have been given to me. Test requirements could say something like, there are some highly critical requirements, you please design test cases to exhaustively test for all the requirements. Test requirement could say something like, you cover this particular fragment of the model or a piece of code, right? So I take these test requirements and refine them with reference to the model that I have in mind. After I refine the test requirements, I have done my test case design, and I'm ready to give my test case as inputs. Remember, once I have a test case, that has to be actually executed in a code. So I assume that I have an implementation ready and I move on to the implementation of the software. Right? Once I have given my test case design, I pass these inputs, make it ready for execution. Make it ready for execution. You remember in the last module we saw this step called test automation. So I do test automation and get the text scripts which are ready for execution. Then I use a tool to execute these test scripts and observe the results. And then I conclude whether the test cases have passed or failed. Right? So this is the normal process of testing that we saw. The only difference here is that while doing designing of test cases, I have a particular model of the software in hand and I design test cases for a set of test requirements on that specific model of the software. Right? Here, my main use of models is to be able to do test case design. Right. So the classical view of model-based testing or model-based design is to say that models could represent a very high-level abstraction of the software. It may not represent the actual code. In fact, code is almost always never represented as a model. Code is represented in the programming language of your choice and is always an executable entity. Models may or may not be executable. They could be static artifacts that represent the code, right? Typically, a model is supposed to capture all the behaviors of the particular software artifact, and it is for the user to ensure that the model of the software is accurate and good enough to meet the required expectations of the model. If the model that you do of the software artifact is itself wrong, then obviously the test case and or everything else that you do with the model is also going to be wrong, right? So it's up to the user to ensure that he or she knows the modeling notation well and has modeled the software well enough to be able to design all the test cases. Right? So we don't view the classical view of model checking in this particular course. We will view model-based testing for doing coverage criteria-based design in this course. Right? So what do? We first focus and represent the software artifact as models. We typically work with several different models. So where do these models come from? So graphs are one kind of models that I want to work with. Where do I get graphs from? I can get graphs from source code. You might have heard of control flow graph or a flow chart corresponding to a piece of code. In fact, there is something called data flow graph, which represents the control flow along with a tracking of the variables that are involved at a particular piece of statement in a code. And then there is a notion of call graph in an interprocedural call graph when the code is modularized into several functions or procedures or methods, right? I can also get graphs from design, right? Lots of designs these days are represented using UML notations, which are basically finite state machines, state charts. All these are some specific kinds of graphs. They have several different specific parameters to each of them, but they're all basically graphs. Another class of models that we will be working with are what are called logical predicates. Where do logical predicates come? If you see a typical code or an implementation is studded with them at every decision point in the code. What is a decision point in the code? It could be an if statement, a while statement, or for statement, right? Which says that there is going to be some kind of branching in the execution of a code, some kind of a choice in the execution of code. At every decision point in the code, there is a predicate. Based on whether the predicate is true or false, the code execution takes one path or the other, right? So what we will try to do is we will try to work with graphs, logical predicates, and a few other things as models of software and design test cases based on these models based on certain criteria. So what are the 4 different models or structures that we will be working with as a part of this course? We will first begin with graphs next week. So graphs typically in software define control flow. They also define data flow. And as I told you a little earlier, they also could be graphs that depict calls of procedures, one procedure calling the other. So we'll look at graphs as models representing such entities about a piece of software, and then we will define criteria based on that and understand how to design test cases based on criteria. Then we will look at logical expressions as they occur in software, as they occur in code, as they occur as guards in designs that are represented as finite state machines, as they occur in requirements. And we will design test cases that check when a logical predicate could be true or when a logical predicate could be false, right? We will also, for the point of view of black box testing, look at sets of inputs that are given to a software and design test cases based on partitioning of those sets. So sets would be another set of structures that we would be working with in this course. And finally, when we look at coverage criteria, we would also look at the underlying syntax of programming language. So every programming language, as you know, it could be C, it could be Java, it could be Python, has an underlying grammar which tells you what is allowed in terms of writing in that programming language, how to write programs in that programming language. And when I compile a piece of software, in the process of compiling, I also check if the particular program adheres to the underlying syntax or not. So you can do mutation testing, which exploits the syntax of a particular piece of programming language and designs test cases by manipulating inputs that adhere to the underlying syntax or grammar of that particular language. So to summarize this slide, what we will do is we will look at software artifacts as 4 different structures or models. We'll first consider them as graphs, and then we'll consider the logical predicates that occur in the code. Then we will look at sets of inputs and outputs, and finally we will look at the grammar or the syntax of the programming languages. For each of these, we will design what are called testing criteria and also see algorithms on how to design test cases to test for these criteria. Right? So here is a simple example to understand what criteria means. Let's say somewhere in your piece of code there is this following decision statement. How does this read? It says if x is less than 5 and a Boolean variable called flag is true, then you do something. Right? We're not interested in what we do. I just want to focus on this particular if statement. Now, what is the label of this if statement? The label of this statement is this particular thing, right? X less than 5 and flag is equal to true. It involves 2 kinds of variables. It involves maybe an integer variable x whose value is compared to 5, and it involves a Boolean variable flag which is tested to be equivalent to true. So this whole thing is what we call a predicate. So let's say suppose this predicate turns out to be true, that is x is indeed less than 5 and flag is also equal to true, then you say that the if statement takes the then branch of the code. And suppose this predicate is false, then you say that the if statement takes what is called the else branch of the code, right? So how will I make this predicate true? So I say you write 2 kinds of test cases, one that makes this predicate true and one that makes this predicate false. That way I would have exercised this if statement for predicate coverage or branch coverage, right? So when I cover a predicate, I also cover the then branch of the if statement when the predicate is true, and I cover the else branch of the if statement when the predicate is false. So for this particular if statement, suppose I set x to be equal to 3 and the value of the variable flag to be equal to true, then the whole predicate with this AND operator evaluates to be true. So this would exercise the then part of the if statement. And suppose I give a value of x to be 7 and let's say I set the Boolean variable flag to be true, then this predicate would evaluate to be false because this first condition will evaluate to be false, right? So then this will mean that this whole if statement will have to exercise the else part of the code that is present after the if statement. So I say this is my test requirement. My test requirement is to be able to achieve predicate coverage on this if statement, and these are the 2 test cases that achieve this test requirement, right? So we'll see how to define such coverage criteria based on graphs, based on predicates, based on sets of inputs, and how to automatically design test cases that will tell you whether the particular coverage criteria is achieved or not, and if it is achieved, how is it achieved? So here are some definitions. So what is a test requirement? A test requirement is basically a requirement that you say about a test case. You give a thing like, please design a test case to cover this if statement, to execute the if statement once for the then part, once for the else part. You might say, please design a test case that will execute this while statement at least 3 times. You know, these are all test requirements. They basically give you requirements on how to design test cases. What is the criteria? A criterion is a rule or a set of rules that impose certain requirements on a set of test cases. Like in the previous slide, if you say my test requirement is to test this if statement to be true once and to be false once, then the criteria is what we call as predicate coverage, right? So given a set of test requirements for a coverage criteria C, we say that a set of test cases satisfies the coverage criteria C if every test case in that set of test requirements satisfies the coverage criteria C, right? There is nothing more to it. So it is to be noted that a particular coverage criteria may or may not be feasible. Like for example, you take an if statement that occurs in something like this. Let's say this if statement is labeled by a predicate that can never be made false. For example, right? It could be labeled by a predicate that is always true or a tautology. In which case, I say that predicate coverage criteria on this if statement becomes infeasible, right? Because predicate coverage says that you make this predicate that labels an if statement true once and false once. But the predicate is such that it can never be made false. If it can never be made false, then I can't achieve predicate coverage. When I can't achieve predicate coverage, then I say that the particular coverage criteria that I can't achieve is what is called infeasible. So it is an undecidable problem to check for an arbitrary coverage criterion whether it is feasible or not. What we will see is several heuristics or techniques that will let you decide implicitly whether a particular coverage criteria is feasible or not, and if it is feasible, to be able to design test cases that will satisfy the coverage criteria. So how do we design test cases that satisfy the coverage criteria? There are two ways to do it. One is to automatically generate test cases that satisfy the coverage criteria. And the next one is to generate test cases externally. Externally means you generate it arbitrarily and then somebody gives you the coverage criteria. Now you take this set of generated test cases and the coverage criteria and you check if these test cases meet the coverage criteria. So that is done by what is called a recognizer. And directly given a coverage criteria, generating test cases for that coverage criteria is done by what is called a generator, right? Both generator and recognizer for testing based on coverage criteria are in their most generality undecidable problems. In fact, several times the algorithms for decidable fragments also have high complexity. But we will look at algorithms nonetheless without worrying about what their complexity is and see how to use them to be able to generate test cases. Right? So now suppose I have a particular thing and I define several different coverage criteria on a particular test requirement, right? So I should know how do each of these coverage criteria compare to each other. Like for example, in a piece of code, I could have two different coverage criteria. One coverage criterion says that you design a set of test cases that will execute every statement once, right? Another coverage criterion says that you design a set of test cases which will execute every branch for the then part and for the else part once, right? So how do I know which of this is better? And the work that I do for achieving one coverage criteria implicitly also meets another coverage criteria. So the notion of subsumption comes to our rescue here. So we say that a particular coverage criteria C1 subsumes another coverage criteria C2 if every test case that satisfies criterion C1 also satisfies criterion C2. Like for example, suppose I told you there was a criteria which says execute every statement once, right? Which means execute every statement in the program. And let's say there was another criteria which says that execute in every branch that you encounter, execute the true part, execute the false part. It is obvious that the first coverage criteria which says execute every statement once subsumes the second coverage criteria, right? Because if I execute every statement once, I would also be executing the statements of the then branch and the statements of the else branch, right? So this is how I use the notion of subsumption to be able to compare coverage criteria. It's important to be able to compare coverage criteria to reduce the burden on you repeatedly generating test cases for different coverage criteria that are actually subsume the other coverage criteria. So it's important to know if I generate test cases for one kind of coverage criteria, what other parts of other different coverage criteria I have already achieved because of this, right? So the notion of subsumption will help you to answer these kinds of questions. Right, one important note to observe is that suppose a particular coverage criteria is infeasible, then I really don't look at what is subsumption for that coverage criteria. I define subsumption only for feasible coverage criteria. So what is the plan ahead for the next weeks? What we will do is that we will consider software as various mathematical models or structures. So what are the 4 structures that I said we will look at it? We look at graphs as models of software artifacts. We look at logical predicates that occur in software artifacts. We look at sets of inputs and outputs that are given to the software. And finally, we look at the underlying grammar or the syntax of software. For each of these models or structures, we will define coverage criteria and discuss algorithms that will let you design test cases to achieve coverage criteria. Of course, we'll look at subsumptions of coverage criteria and so on and so forth. So what we'll do first is we'll look at the model at an abstract level, just as a graph, as a predicate, and then define algorithms for coverage criteria. Post that, we will look at various software artifacts. So we will see how to take code and model it as a graph. And what are the coverage criteria that we looked at graphs, and how do those help to test various aspects of the code. Then we'll take design and model it as a graph. And then we'll see what are the coverage criteria that we looked at for graphs that will be relevant to design test cases for this design. So similarly, when we go to logical predicates, we'll look at logical predicates as they occur in code, look at coverage criteria, and then see how these coverage criteria means testing which parts of the code, right? So we look at these mathematical structures, look at coverage criteria separately, then we look at how to model software artifacts using these structures, and what do the various defined coverage criteria mean for these structures, right? So next week, when I begin my first module, we will look at graphs as models of software artifacts and define coverage criteria based on graphs. So that will be the next lecture. Thank you.